You have seen my lecture about the resources and processes involved over the lifetime of a nuclear power plant. It is now time to discuss the economics of nuclear energy production. I am Sara Boarin. Let's dive in. We will start with some key economic indicators. The levelized cost of electricity is the unit electricity generation cost, and it is widely used for comparing costs of different power technologies. The lower the LCOE, the better are the project economics. The net present value is the total value generated by a nuclear power plant during its entire lifetime. The internal rate of return is the profitability ratio of the nuclear power plant project. Cash flows generated by the project are compared to the capital investment. The payback time is the time when cumulated earnings from the nuclear power plant equal the cumulated costs. In order to calculate the NPV, all the cash flows, both positive and negative, are considered, discounted and cumulated. The internal rate of return is the interest rate that breaks even the NPV. In the discounted cash flow approach, LCOE may be calculated as the electricity price that breaks even the NPV. Here, nuclear power plant 1 in red has better economics than plant 2 in blue, since the cost of a unit of energy is lower. A higher discount rate decreases the NPV and increases the LCOE. The discount rate is the cost of capital that represents the remuneration rate required by investors. It reflects the risk perception by investors. When future cash flows are less certain, investors ask for a higher remuneration rate. The project risk increases with longer payback times. Capital costs, which include construction and interest, represent the predominant share of the LCOE from a nuclear plant. Almost all the components of the nuclear LCOE are fixed, except for fuel cost and few consumables used in operation and maintenance. The LCOE varies significantly by country, since a relevant part of the construction cost is country-specific: salary, nuclear safety regulation, local supply chain, and so on. As said, higher interest rate increases the LCOE. You can see the effect of the interest rate in the figure on the right. The LCOE may be calculated without a DCF approach, as the lump sum of all the cost components annualized: construction, operation, decontamination and decommissioning, fuel. A constant equivalent cost annuity is calculated and divided by an average annual electricity output in megawatt hours. The LCOE can be viewed as the minimum constant electricity price that covers all the costs and breaks even the project. In this case, the cost of capital and the decontamination and decommissioning are accounted in the construction cost component. Construction costs are sunk costs for investors and have to be recovered by means of the sale of the electricity produced. Any factor that may compromise the revenue stream is a risk factor. As an example, plant availability, market price volatility, electricity demand, and so on. The revenue stream has to be maximized, and this pushes towards the maximization of the capacity factor. This is why nuclear power plants are said to be price takers. Nuclear power does not play a role in setting the price on the electricity market, since it has to produce power at full regime and cannot play on flexibility like generation technologies that have predominantly variable costs. Here, a sensitivity analysis on the LCOE is provided. Each input is increased and decreased by 50%, and its impact on the LCOE is calculated separately. The percentage change in the LCOE is represented in the graphs on the screen. The most sensitive parameter is the financial interest rate. Construction cost overruns and construction lead time are major concerns, since these can seriously undermine the nuclear project economics by deteriorating the profitability and increasing the LCOE. The Generation 4 International Forum has defined a comprehensive code of account of total capital investment costs. That is a cost breakdown system. according to this code, half of the total construction costs are capitalized direct costs that include equipment, on-site direct labor, and commodities such as wire and concrete. Main components of direct costs are civil and reactor equipment, including the steam generator and turbine equipment. Total direct costs may also be divided into nuclear island costs, some 40%, and balance of plant, which includes all the residual systems and equipment. The economy of scales apply to capital cost of all industries and even to single pieces of equipment with different specific coefficient F in the formula. The principle is as follows. If the plant size increases in terms of output, total cost increases less than proportionally with respect to the plant output. Therefore, unit construction cost is expected to be lower for a large plant compared to a smaller one, instead of being constant. Economy of scale significantly reduces the expected total cost of a large-sized plant. The effect of economy of scale is relevant in the nuclear industry, where capital construction costs are very high. This is the reason that push towards the maximization of the size of nuclear power plants throughout history. However, could there be a minimum in the economy of scale curve, a size beyond which this economy of scale starts to apply? For now, this is still an open question. The fuel cycle costs are divided in the front end, containing the uranium supply, conversion, enrichment, and fuel fabrication, and the back end, which contains reprocessing, conditioning, and final geological disposal. They vary widely with the fuel cycle strategy, one through or reprocessing. Disposal costs depend on geological conditions and on the repository features, and until now no industrial reference costs are available on this topic. Normally, a decommissioning and decontamination sinking fund is established during the plant's operating lifetime that sometimes can be invested in high-grade tax-free bonds to accumulate the funds necessary for decommissioning. The sinking fund formula indicated here can be used to calculate the annual payment to the D&D fund. At present, no universally accepted standard is established for developing decommissioning cost estimates, which vary depending on the D&D strategy, the scope of activity, the final state of the site, the plant type, and so on. Due to the actualization effect on long-term expenses, the D&D component in the LCOE is negligible.